Welcome. In this talk we will take a deep look at the Shark engine that drives pretty much all ORCA calculations starting from ORCA 5.0. Shark originated from an idea that I had in 2015 how to reformulate molecular integrals, but it became something much bigger, and it was not until the lockdown month that finally it came to life. So what is Shark? Shark is a completely newly developed library for highly efficient generation of 1 and 2 electron integrals, but it is also a task driver that in a very efficient and lean and simple way drives quantum chemical tasks like Fock matrix formation, integral transformations, and so on. It is also a new paradigm for quantum chemical code development that we will use extensively in the future. So ORCA 5 is like the first realization of it, but we will go much further with it in the future. As a user, you don't really see very much of Shark. You will see a new banner when the integral calculation comes up, but beyond that, there's only a printout here and there, but internally, practically everything is driven by Shark. So now let's take a look at the heart of it, which is the integral algorithm. Quantum chemistry centers around the calculation of integrals over basis functions, and there are 1 electron integrals of various kinds. The 1 electron integrals like overlap, kinetic energy, nuclear attraction, but then property integrals like dipole, field gradient, spin orbit, and so on and so forth. And there also is, and that is really where the bottleneck is, a large number of 2 electron integrals that one needs to calculate, foremost the electron-electron repulsion integrals, but then also finer, more complicated integrals like the spin-spin integrals, the spin-orbit integrals, GIAO integrals, F12 integrals, and so on and so forth. And now we need efficient algorithms to compute these, and this is the bottleneck of all modern quantum chemistry. Now, integrals are used in a number of tasks. Perhaps if you do DFT or Hartree-Fock theory, the Fock matrix formation is the most important one that consists of 1 and 2 electron terms. But then there are also other terms where you extensively use integrals in integral transformations, in sigma vector formations, for example for TD-DFT or also for CPSCF, and then in a number of property calculations. So it is of absolutely utmost importance that this integral generation is as efficient as possible. Now, for many reasons, practically all modern quantum chemistry uses Gaussian basis functions. As you see here, Gaussians have 2 properties that are quite undesirable. A, they don't have a cusp at the nuclear position as they should have, and B, they fall off much too steeply. So in principle, Slater orbitals would be a better choice, but integrals over Slater functions are almost impossible for multi-center integrals to generate efficiently, hence Gaussian basis functions. Now, the nice property of Gaussians is if you take a product of 2 Gaussians as they occur in practically all molecular integrals, the result is again a Gaussian function, and that Gaussian function is centered somewhere midway between the centers of Gaussian A and Gaussian B by means of the Gaussian product theory. So that means that 4-center integrals are being turned into 2-center integrals that are much easier to calculate. Still, there is something that is quite nasty, and so if you have basis functions with angular momentum larger than 0, you have a polynomial that multiplies these basis functions. Now, if these polynomials are centered at different points in space, the resulting product Gaussian has a very nasty polynomial that is difficult to integrate. And now here McMurtry and Davidson had an ingenious idea, and that ingenious idea was to expand that nasty polynomials in terms of a set of complete polynomials, and namely the Hermite polynomials that you all know from the harmonic oscillator problem. And so what that means is that you can expand that nasty polynomial in terms of these nice polynomials centered at the midpoint. And the expansion coefficients are these E coefficients that are readily generated by a recursion relation. Now that leads to the famous McMurtry-Davidson formula for 2 electron integrals. It is really a thing of utmost beauty, and it leads to a very strongly nested 6-fold sum over these various intermediates where the E coefficient provides a transformation from the Cartesian Gaussian basis into the spherical harmonics basis, and these R's that you see in the formula, these are the actual repulsion integrals over the Hermite polynomials, and for them also recursion relation exists. So the key idea of Shark is to not perform these six-fold nested summations, but to do it more efficiently and more leanly by means of matrix multiplication. So if you look at this equation, then you can imagine that the e-coefficients for the bra form a matrix and the e-coefficients for the cat form a matrix, and then the Hermite integrals also form a matrix. And these indices here are TUV for the Hermite Gaussians and mu nu for the Cartesian Gaussian. And that means you can reformulate the McMurtry-Davidson integral algorithm in terms of two matrix multiplication. So you generate the R integrals and then you multiply them from the left and the right with the E coefficient, like the E matrices for the bra and the cat. And that has a number of key advantages. A, it leads to a factorization of the integrals, and that allows for redundant work to be eliminated. For example, you can fold the spherical harmonics transformation when you do the calculation in spherical harmonics, as we always do in ORCA, and you can fold that into the E-evaluation that you do at the start of the calculation only once. And then you have the incredible power of the BLAST level 3 operation to finally do the contractions that lead you to the final integrals. And that is an extremely simple and efficient implementation that you can base on it. Just to remind you, the extremely strong power of the BLAST libraries, if you code a matrix multiplication by hand and compare that to the most efficient vendor-optimized libraries, you will find that the vendor-optimized libraries are at least a factor of 5, but up to a factor of 50 more efficient than what you can code by hand. So whenever you can, you should formulate quantum chemical algorithms in terms of matrix multiplications, and that will drive your hardware at peak performance. And so this is where Shark really wins. Now here is the first implementation. This is a slightly old slide, and we compare Shark to Libin, and so you see that for low angular momenta, basically all algorithms are good and efficient, but for high angular momentum, Shark wins dramatically up to a factor of 5 over traditional algorithms. And Shark also takes advantage of contraction, because some contraction steps can also be moved outside the innermost loop, and that means you have a super highly performant algorithm. There are intermediate angular momentum cases where the traditional algorithm wins, and that's why what we have implemented in ORCA 5.0 is a hybrid between Libin, which is optimal in terms of flop count, and Shark, which drives the computer at peak performance using the BLAST operation. And this is how that looks in practice. So after a lot of optimization, we can compare here ORCA 4.2.1 that uses Libin exclusively and ORCA 5.0, and you see that in all integral transformations, the new algorithm is a fair bit faster. It can be 20%, 30%, but it can range up to a factor of 5, full factor of 5. And that obviously leads to very large performance gains in the actual calculation, but it is not exactly the integral gains that you see in the final results, because at the same time, we have re-optimized our integration grids. They are larger and more accurate, but they cost more time. And so that's why what you see here in the actual total Fock matrix formation times is that we have reinvested the time that we have gained in the integral formation into a more accurate algorithm for the Fock matrix formation. And so overall, ORCA 5 is still faster in the Fock matrix formation, but it is not that dissimilar from ORCA 4.2.1. You will see the largest gains for large basis sets, quadruple zeta and larger, where the integral calculation really dominates, and there is where key advantages are. Now, this is not the only thing. You don't only need to generate these integrals, you only need to digest these integrals into the various quantities that I've shown, like Fock matrices or transformed integrals. And here we have also spent major efforts to make this more efficient by reformulating that in terms of BLAST operations, and that really kicks in when you not only form one Fock matrix like in SCF, but when you form many Fock matrices at the same time, as you do in TDDFT, CIS, response calculations, CPS, CF, and a number of other tasks. And that leads to really dramatic speed ups. Now, when you compare here TD-DFT calculations on a reasonably large molecule, you will find that for a large basis set like DEF2-QZVP, the new algorithm is actually up to 10 times faster, and that is 10 times faster in the actual wall clock time, the time that you have to wait for your result. But overall, even for a triple zeta base set, it's easily a factor of 2 to 5. And these are gains really worth having, and that leads to ORCA 5.0 being a much more efficient program than previous ORCA versions, and we're proud of it, and I hope very much that you as a user will experience this increased performance, and you will like it and you will use it. Now, another thing that we have done in the development of Shark that is important is that we have taken care of all kinds of basis sets. So traditional Gaussian basis sets are not done in a primitive Gaussian basis where each basis function is in single individual Gaussians, but by contractions of Gaussian functions. And most basis sets, for example the DEF2 basis sets, they are in a so-called segmented contraction where each Gaussian primitive only contributes to a single final basis function. Now, that is done efficiently by traditional integral algorithms. But then there are also the polar opposite is the so-called general contractions as in A and O basis sets. And here every primitive on a given atom and angular momentum contributes to all basis functions of that atom and angular momentum. And in order to avoid redundant integral calculations that would make these calculations super expensive, you need to develop algorithms that explicitly take care of the general contraction, and we put major efforts into that, and that's why ORCA 5.0 performs very, very well for generally contracted basis sets. Now there's a third type of basis sets that is met in the correlation consistent basis sets, and they are partially generally contracted, meaning that some angular momentum on a given atom are generally contracted and other functions are left uncontracted, for example, the polarization functions. And it is quite complex to come up with an algorithm that performs optimally for this type of basis set, but that is also something that ORCA 5.0 specializes in, so there are special algorithms for these partially generally contracted basis sets. Now, as a user, as I said, you don't see much of Shark, and we don't let you manipulate a lot of it. There are a few flags that you should be aware of that you can use. So first of all is the flag use Shark or no use Shark to turn it on or off. So you can run just the same way as you did in the old ORCA if you want to check. This will disappear in future ORCA versions. Future ORCA versions will exclusively use Shark. But for this version, you have the option to turn Shark on or off. Then there is a print level. By 0 means no output, 1 means the default output, 2 gives you some more information, and 3 and 4 are just debug prints that I don't recommend you to use. Now there is a fog flag, and that fog flag that determines which algorithm is triggered. You can either use force Shark to calculate all integrals with Shark, or you can use force libin to calculate all integrals with libin, or, and that is the default, a Shark libin hybrid, and that chooses the most efficient algorithm for each task and each class of integrals. Finally, there is a partial GC flag, and that turns the handling of the partially general contracted base sets on or off. The default is -1, which means that the program will automatically decide which is the best algorithm. You can force the partial general contraction to be off by choosing 0 for that flag, or 1 to enforce it, even if you have an A and O basis set. And finally, you can use the flag use general contraction true to enforce the algorithm for general contraction, even if you have a segmented basis set. I don't recommend that, because for segmented basis sets, the standard algorithm is faster, but you have control over that. And in principle, you don't need to touch any of these variables because the program by default will choose the right algorithm for you. Now, finally, there is the Shark task driver. And what that means is the following, and this is really why Shark is so much more lean and efficient than the old code. So this is a snippet of the old ORCA code, and it consists of many places where you set up integral loops over basis functions, and then you organize that calculation, and then you calculate the integrals, and then you digest the integrals. And whenever you do something new, a new type of Fock matrix or response matrix or whatever it is, then all of these loops have or were reprogrammed in the past, leading to tens and hundreds of thousands of lines of code. And if you want to change anything, you need to change it in all of these hundreds of places where this occurs. And that, of course, is in terms of programming not the most efficient. And we have found a way in Shark to boil these tens of thousands of lines of code down to just a few. So the programmer only programs a little object that digests these integrals and does something with them. And the entire Shark engine takes care of streaming integrals towards that digestion algorithm. And that means that you can set up these integral loops in a very efficient manner with just a few lines of code where you had to write thousands before. And that means there is no more code duplication. The development is much more efficient. And then that also means it's far more robust, since there is less code that you have to debug, and that code is also more readily maintained. So this is a major step forward, and you will take advantage of that, and you will see that by us being able to develop much more efficiently than in the past. Now, here is the future of ORCA. So the future of ORCA will consist of all of the numerically intensive stuff, meaning all of the nitty-gritty will be handled by Shark, and Shark is well encapsulated from the rest of ORCA. ORCA will orchestrate the entire calculation, will make sure that the data flows in the right direction, and that all the tasks are performed in the right order, and all of these things, input, output, flow of logic, and so on and so forth. And then, of course, there is a next layer. So we create a shell structure here, and that next layer is the compound job facility that you have learned on in the talk by Dimitris Liakos, and there are also workflow solutions like Wiesel that the company Facts offers. And finally, there is a graphical user interface that at some point it will appear also for the academic world, where we will have a fully integrated graphical user interface. And there is communication between all levels, but it's important that this is well capsulated and hidden from the user so that there is a minimum amount of possibility for error. So that is basically what I had to tell you. And here's my summary. So Shark is an efficient integral algorithm. It performs up to a factor of 5 better for certain integral classes in the old code. It makes near optimal use of BLAS level 3 operations. It takes advantage of contractions. It achieves efficiency by loop unrolling. It makes use of integral factorization, and it provides a clean, easy way to do quantum chemical programming. And Shark is not only an integral engine, but also a task driver for complex quantum chemical tasks. And that means Shark will be the major motor to drive ORCA calculations in the future. Now, I want to acknowledge a few people here. The Shark code was almost completely written by myself, but it had very important contributions. Frank Venmos contributed some key ideas here, especially the object, the virtual function-driven integral loops. That was Frank's idea. Ute Becker took care of all of the parallelization in a wonderfully efficient way. That was a pleasure to work with Ute on this. Georgi Stoichev has helped a lot with the code, and he made many useful comments. He also was the earliest adopter of the Shark integral environment and used it in his development. Benjamin Helmich-Paris was the one who had that really clever idea for the partial contraction algorithm, and so basically what is in Shark is Benjamin's code that he has provided for it. Kantar Ruben Silverlingam has taken care of the CAS-SCF part of Shark, so where it is used, and the entire ORCA development team has helped very much in debugging, discussing, giving new ideas, giving input, evaluating what was there. So I hope very much that you will enjoy that in the future and you will enjoy ORCA 5. And maybe we have a few questions that we can discuss together. Thank you very much.